This is the magnetic field tutorial presented by DSC Charles VB. Hello, welcome to a new tutorial presented by DSC Charles VB. In this tutorial, we're going to see magnetic fields. Magnetic fields, you need to know that the different interactions which are involved here in case of magnetic fields are going to be the magnetic poles, and the magnetic poles are mainly separated into two main parts. You have the north pole and the south poles. Now, magnetic fields, the magnetic fields are not entities or properties which directly come from atoms, like in cases of gravitational fields and electric field. You need to know that the gravitational field directly comes from the mass of an object. Electric field directly come from the charge which is inside the atoms, which is these are the fundamental particles of the atoms. But the magnetic field is produced due to something. So we need to know the origin of magnetism. Now, there are certain particular objects which can be magnetized and others not. The question is why? The answer can be very easy. We need to know that most of elements which can be magnetized are found as transition metals, and the transition metals are d block elements. The d block elements contain electrons found in the d subshell. There are 5 d subshells with 10 electrons which can be found inside. Now, these d block elements consist of scandium, titanium, which can be magnetized, consists of scandium, titanium, vanadium, chromium, manganese, iron, cobalt, and nickel. So these are the main you have scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel. So these are the main ones which can be magnetized. The other one, zinc, is not magnetized. So we have cobalt, nickel, and we have copper at 9th position. So copper can also be magnetized, but the last one, which is zinc, is not magnetized. Zinc is not magnetized because all the electrons which are inside the d subshell are going to be paired, while in cases of each of the elements above here, one of the electrons is unpaired. Now let's visualize why the unpaired electron is going to cause magnetism. So now let's explanation. We need to know that when electron move, they are going to have a spin quantum number, and that spin quantum number is what is effective for the production of the magnetic field. As electron move, there's always going to be a magnetic field which is going to be produced perpendicularly to the motion of each electron. Now, when you have in case of zinc, all the electrons are paired. So since the electrons are paired, this electron is going to move in this direction in a particular orbital, and the other electron are all the spin quantum number of different orbitals of electron in different orbitals are always in opposite direction. So two electrons are going to move always in opposite direction. So when a particular orbital is paired, it implies that the electrons are going to move in opposite direction, and thus the production of the magnetic field are going to cancel each other. This is why zinc does not have a magnetic field produced when it is magnetized, while all the others which have lone pair of electrons in one of the orbitals, scandium, titanium, vanadium, chromium, manganese, iron, cobalt, nickel, and copper, all of them can be magnetized, though their power magnetism can change depending on if they have more unpaired electrons. So now let's visualize now the cases of domains. In normal materials, in normal metals, you have different domains. The atoms here have different domains. Let's say we have this domain here contain, the domains are regions of material which contain electrons moving in same direction. So this domain here is going to have a magnetic dipole moment in the same direction. So electrons are going to move here and they're going to produce a magnetic dipole moment. Electrons are going to move and they're going to produce a magnetic dipole moment up here. Electrons are going to move here and they're going to produce a magnetic dipole moment here. And electrons are going to move and they're going to produce a magnetic dipole moment down. All these are going to combine up. The magnetic dipole moment of different domains are going to combine up and going to cancel out with each other. This is why in normal materials which are magnetized, they don't produce magnetic fields. This is because their domains with the magnetic dipole moment cancel out each other. Now, upon magnetization, what is magnetization? Magnetization is a process whereby a material is given and it maintains its magnetic property. So now we have two magnetic materials. We have weak magnetic materials and we have strong magnetic material. Weak magnetic materials are materials which can easily gain its magnetism and also easily lose its magnetism. Example, iron. We also have copper. Copper is not only a weak magnetic material, but it's also a paramagnetic material because it is very fast in losing in magnetism. So this weak magnetic material where iron is found are called ferromagnetic material because though iron is a weak magnetic material which loses its magnetism very fast, copper is a paramagnetic material which loses its magnetism faster than iron does. We are also having strong magnetic materials. Strong magnetic materials, these are materials which can be magnetized, are difficult to magnetize, but once again in magnetism, they are going to be hardly lost their magnetism. Example is steel. Now, upon having a process of magnetization, you see that a B field is going to be causing all the dipole moment in different domains to be aligned in one direction. So this alignment of the dipole moments in one direction is going to cause the material which have this domain to have an intrinsic property of producing its own magnetic field. So now let's see the law of magnetization. The first law of magnetization is that like pole repel and unlike pole attract. That's the first basic law. The second law is that the force of attraction or repulsion between the two magnetic poles is directly proportional to the strength of the pole. The strength of pole Pn is going to be the strength of the north pole and P is the strength of the south pole, and it's also inversely proportional to the square of the distance separating them. So it's also respecting the inverse square law. But in the case of the conductors which are going to produce their magnetic field strength, they don't respect the inverse square law because only direct inverse proportional to the distance separating the conductor from its surface. So now we are going to see F is equals to is direct proportional to Pn Ps all over R squared. So this is a constant where K is an element of R. So here experiment has shown that K is equals to mu 0 all over 4 pi. So F is equals to mu 0 Pn Ps all over 4 pi R squared. So now the unit of P is going to is given as ampere meter, where P is going to be the strength of each pole. Pn is the strength of north pole and Ps is the strength of south pole. Magnetic flux and magnetic flux linkage. The magnetic flux, consider the magnetic flux and magnetic flux linkage are defined as the number of magnetic material which are going to pass through perpendicular and area A. So this refers to a number of magnetic material cutting through an area A when the direction of magnetic field is perpendicular to the direction of the area. Or it can be defined as a number of magnetic field lines which pass through which are going to pass through an area number of magnetic material defined as a number of magnetic field lines passing through perpendicularly an area A. Now you need to know that this magnetic flux is measured in Weber and 1 Weber is equals to 1 times 10 raised to the power 8 magnetic field lines. So because the magnetic flux are number of magnetic field lines, and they are measured in Weber, and this Weber is equals to 1 times 10 to the power 8 magnetic field lines. The magnetic field strength, which is B, is measured in Tesla. So now the magnetic field, provided that you have this diagram, you see that the B field is going to pass as such here. The angle theta is taken with respect to the perpendicular, because they are saying that it's the number of magnetic field line passing through number of magnetic field line produced when a magnetic field strength passes perpendicularly to a surface area A. So this case, you see that you are going to have a perpendicular area, and this theta is going to be with respect to the perpendicular. So this part is going to be B cos theta, and this is going to be the perpendicular component. So the magnetic flux is going to be equal to B perpendicular component times A. So magnetic flux is going to be B cos theta times A, and we are going to have BA cos theta. Now to find the magnetic flux linkage, we are going to instead have here number of turns of areas. Let's say you have coils, we have different number of turns, and so the magnetic flux linkage is just equals to the magnetic flux times the number of turns, as easy as that. So when you have different number of turns here, the magnetic flux is going to be times the number of turns. The magnetic flux linkage, the magnetic flux times the number of turns. Now let's visualize the Earth magnetic field. Now the Earth magnetic field is produced when due to the Earth crust magma. We see that inside the Earth crust, or inside the Earth core, we have magma inside it, and we also have different radioactive material which produce this magma. All these radioactive material and magma are what influences the production of the North Pole and the South Pole of the magnetic field. Now a point to note is that the magnetic North Pole, this is the magnetic North Pole is going to be located at the level of the South geographical pole. A point to note is that the magnetic North Pole is located at the South geographical pole, and the magnetic South Pole is going to be located at the North geographical pole, and this is proved via experimental analysis. If you take a compass, and the compass will always point toward the direction of this is shown by experimental analysis. So the pointer of the compass is always going to be on the North Pole, and this is going to show you the South geographical pole. So when you have a pointer, a compass, the compass will normally point on the magnetic North Pole, and that position of the magnetic North Pole is going to show you the South geographical pole. So now this is what one has to take in consideration when you want to go to the North Pole and the South Pole. So when you want to go to North Pole and South Pole, you need a compass, and this compass is going to align with the Earth magnetic poles. So the compass North Pole is going to align to the magnetic South Pole, and the compass South Pole is going to align with the magnetic North Pole. So this is why since the compass North Pole aligns to the South Pole here, so the compass North Pole is going to show you the North Pole. So this is the first consideration that you have to take when you want to use a compass. Number one. The second consideration when you want to use a compass is the deviation between the magnetic South Pole and the North Pole. You need to know that there is an angle of deviation between the magnetic South Pole and the North Pole, and this angle of deviation is called the angle of inclination. So when a ship is navigating through the North Pole via using a compass, there must always be a protractor on the chart in order for you to measure the angle of deviation. This is why in most films you realize that the ship or mariners at first use protractor to calculate the angle in order for them to go at effectively in the North Pole. Else, when you are going to move with the compass, it's going to make the ship move in this direction. Now, taking into consideration, this is where the ship is going to move when it's going to move to the North Pole. Taking into consideration of angle of deviation, as it is calculated, the ship can change its track now and go to the true North Pole, which is the geographical North Pole. So this is how the angle of inclination is used. Now let's visualize what is the angle of dip. The angle of dip is the angle at which the magnetic pole is going to penetrate this Earth's surface. Angle of dip is defined as the angle at which the magnetic field lines penetrate the Earth's surface. Now, the angle of dip can vary at different regions of the Earth's surface. So, this in the equator you have different angle of dip. In the poles you have different angle of dip. At the poles you mostly have an angle of dip of 90 degrees, and at the equator you mostly have an angle of dip of 0 degrees. So angle of dip can enable one to know its position on the Earth's surface. Now let's visualize the force acting on a charge. We need to know that for a magnetic force to act on charge, the magnetic field strength must be perpendicular, must have a component perpendicular to the direction of motion of. There are different conditions involved before a magnetic force act on a charge. So before you start in order for you to employ the magnetic force acting on a charge, you need to know certain conditions in your mind. So the first condition is that, number one, the charge must be moving. Point number one, the charge must be moving. If the charge does not move, then the magnetic force will not act, though a magnetic field strength is present. So number one condition for a magnetic force to act on a charge is that the charge must be movable. Point number one. Number two is that the magnetic field strength must have a perpendicular component to the direction of motion of the charge. If the magnetic field strength does not have a perpendicular component and it is solely parallel to the direction of the moving charge, then there is no force which is going to act on the charge. Now, taking all this into consideration, the magnetic force is going to be given as a vector where we are going to cross. We are going to cross this V vector cross B vector in this direction. It is not B cross V, it is V vector cross B vector times the charge. So when taking all this into consideration, the magnitude of F cross V cross B is taken as F magnitude equals to cure V magnitude B magnitude sine theta. So F is equals to B cure V sine theta. So now let's say you have this case, a magnetic field is moving out of paper, and we have a velocity v moving as such here. So this is the velocity v. So an electron is moving as such and entering into a magnetic field which is out of paper, perpendicular to the which is perpendicular to motion of the charge. So it's going to cause now a motion in this direction here. So we need to know that in the first case, when we have studied electric fields, we realize that when the electron entered into the capacitor plate, the motion which was produced was a parabolic motion. So in electric fields, as electron move in electric field, the motion produced will follow a parabolic path. But when charges or electrons move inside a magnetic field, they are going to follow a circular path or a helical path, depending on the angle at which the magnetic field and the velocity are found with respect to each other. So here we are seeing a circular motion. In the latter section, we are going to visualize a helical path, a helical motion. So in case when the velocity is solely perpendicular to the magnetic field strength, then we are going to have a circular path. But when the velocity is not solely perpendicular and the magnetic field strength has both a parallel component and a perpendicular component to the velocity, then it's going to produce helical path. So in this case, you're in a circular motion, you see that there is going to be centripetal force which is going to be produced, and that centripetal force is going to be solely equal to the magnetic force. So now we say that Fc is going to be equal to the magnetic force. So Fc, we know that is equal to mv squared all over r. Mv squared all over r will be equal to the magnetic force b curve. We don't use b curve sine theta because here the angle in this case between the magnetic field which is perpendicular to paper and v is going to be 90 degrees. Sine 90 degrees gives 1. So we use b curve. So when we have this, v is going to cancel here and say r, which is going to be the radius of the radius that is going to be produced here, is going to be equal to mv all over bq. Now this radius of curvature is used in order for you to know the path that the alpha particle, the beta particle, and gamma radiation are going to have when they are going to move in the perpendicular magnetic fields. We know that r is equal to mv all over bq, and we also know that the alpha particles are going to have a mass, an atomic mass of 4, an atomic number of 2, and the beta particles have atomic mass of 0 and the atomic number of -1, while gamma radiation have 0, 0. So in this case, we need to ask ourselves which one is going to be which among all these are going to be highly deviated by the magnetic field. For the magnetic field to cause a high deviation, then the radius of curvature needs to be very small. If the radius of curvature is very small, then the deviation that is going to be produced by the magnetic field on each of the particles is going to be very high. So we are going to visualize now each cases for you to have the radius of curvature area to be very small. So now alpha particles have a very large mass. They have a very large mass, and their charge there and with respect to their corresponding charge, you see that since they have a very large mass with respect to corresponding charge, here is mass and here is charge. So when you place mass here, I'm going to place charge here, you see that the factor is going to be smaller. So the factor, you are going to have a radius of curvature since the mass is going to be larger than the charge. So you see that the radius of curvature is going to be large. Since the radius of curvature is large, it implies that the deviation is going to be less considerable. It's not very highly considerable. So alpha particles are not going to be highly deviated by magnetic field, by magnetic field. Now let's visualize for beta particles. Beta particles say that the mass is very negligible while the charge is considerable. It implies that when you substitute the mass here and you substitute the mass is going to be very small and the charge is going to be very large. It implies that the radius of curvature is going to be very small. Since the radius of curvature is very small, it implies that the beta particles are going to be highly deviated by the magnetic fields. Now let's visualize the other case in case of R. So in case of gamma radiation, in case of gamma radiation, we see that the velocity of gamma radiations is the most extreme velocity known. Gamma radiation are electromagnetic waves, and the velocity is going to be 3 times 10 to the power 8 meters per second. Since the velocity is very high, so the rate of curvature is going to be very high, and thus the deflection is going to be less considerable. So comparing all this, you see that gamma radiation is the least deflected by magnetic field. Then the alpha radiation, the alpha particles comes the second, and the first, the most deflected by the magnetic fields are beta particles. So now let's find the period. In order to find the period, see note that the centripetal force is going to be equal to the magnetic force. So m omega squared r is equal to b curve v. So omega squared, we are going to have omega squared is equal to, we know that B curve V all over MR. Now we know that R is equals to MV all over B curve as it was calculated up here. So when we substitute, we are going to have B curve V all over M times B curve all over MV. So omega squared is going to be equals to B squared Q squared all over M squared. So omega is going to be equals to B Q all over M. So now we know that omega is equals to 2 pi all over T all over period when seen in classical mechanics. So 2 pi all over T is equals to BQ all over M. So now T, it will imply that by cross multiplication T is equals to 2 pi M all over BQ. So now the total force on the charge moving in electric and magnetic field. So let's visualize total force. So this is the period. Here is the period that this motion is going to have. So now let's visualize the total force acting on a charge moving in both an electric field and a magnetic field. So the total force, which is the resultant force, will be equal to the electric force in the parallel direction to the motion, and plus the magnetic force in the perpendicular direction of the motion. So the electric force given as Q electric field, and this is given as Q V cross B. So when you have this, this is the total force that's going to be produced. Now let's visualize the Hall effect. In case of the Hall effect, the resultant force is going to be 0. But the resultant force is going to be 0. That is, there is no acceleration. But we need to know that with Hall effect, there is going to be the charge is going to move with a continuous velocity. Let's say that you have this charge which is moving. This charge is going to have an electric field acting in this direction, a B field acting in this direction, perpendicular to the motion of the particle. The particle is going to move in this direction, so the B field is perpendicular to it. So you are going to have E is going to cause an electric force in its direction. So we have electric field going to cause the electric force in this direction. I have the magnetic force going to cause an opposite magnetic force due to the motion here. So if at the Hall effect, we need to know that the resultant force is going to be 0. So since the resultant force is going to be 0, it implies the Fe is going to be equal to negative Fm. Now for the magnet, you know to know that for the condition of magnetic force to occur, then this charge should be continuously moving. If this charge stops immediately, then there will be one force in the system acting, which is only going to be equal to electric force. So the charge is going to have a 0 acceleration, but it's going to have a constant velocity in this direction. So we are going to have Fe is equals to Fm. So since Fe is equals to Fm, it implies that Q is equals to BQV. So now Q and Q cancel, you have E is equals to BV. So this is the case where of Hall effect. Now we know to know that if you are the electric field now is produced by capacitors, by parallel plate capacitors. So the electric field is given as the voltage of that capacitor divided by the distance between the plate. So when you substitute it, you are going to have QV all over D is equals to BQV. So V is equals to BDV. So now let's find now the magnetic field strength if the electric field is given. So magnetic field is instead going to be equals to B is equals to B all of E all over V. And if the electric field is given in terms of voltage and distance separating the plate of capacitor, so B, the magnetic field, is going to be equals to voltage all over the velocity of that charge times the distance. This is why I initially told you that though there is no resultant force, though it is said here that there is no resultant force existing on the charge, there is going to be a constant velocity which is going to act. Note that by Newton's first law said that a body will continue in a state of rest or uniform motion provided that no external force acts on it. So a body which is in uniform motion or uniform velocity has no acceleration which can occur on it. So in this case, here you have no resultant force. Here resultant force equals to 0, but the velocity is constant, and this is what is going to be enabling you to calculate for the E here, which E equals to BV, and calculate the magnetic field strength B is equals to E all over V. So now let's find now the velocity. The velocity is going to be equals to, so since you know that Q is equals to B QV, the velocity is equals to E all over B. Or now if you have the electric field produced by the capacitors, where the voltage across the plate of capacitor equals to V and the distance separating the plate of capacitor is D, then the velocity is going to be V all over BD. So now in the first case, you have visualized the force, the magnetic force acting on a moving charge. Now let's visualize the magnetic force acting on current carrying capacitors. So now we know that I is equals to dq all over dt, but for when the current is constant, I is equals to q all over t. So now this is going to be the electron flow. Let's say that the electron flow in this direction and current flow in this direction. Let's say the magnetic field is perpendicular to the current flow. So this is the angle theta here, and this is F here. So let's prove now for the formula of the magnetic force acting in a current carrying conductor. We first know that the formula for the magnetic force acting on an electric charge is given as Fm is equals to BQV sine theta. So now this is equals to, we know that V is defined as L all over time, so the distance divided by time. Now in this case, this L here is the distance, the length of the conductor is going to be the distance, and you have the time too. So now when you are going to put it, this and this are equal, so this is equals to BQ all over T L sine theta. But we know that Q all over T is equals to I, so it implies that the magnetic force acting now on the current carrying conductor is equals to the magnetic field strength times the current carried by the conductor times the length of the conductor sine theta, and that theta is the angle the magnetic field does with the direction of the current which is being carried. So now this formula resembles the formula that we had initially, the vector formula of the force, magnetic force acting on a charge. Fm is equals to QV cross B. Now in this case, you are instead going to have Fm is equals to L into I, the current, cross the magnetic field strength. So now what are the let's visualize the formula of magnetic field strength of different materials. Now for current carrying conductor, you have different formula involved. Current carrying conductor, you have the formula for outside the current carrying conductor, you have for on the current carrying conductor, and inside the current carrying conductor. Now these are the different cases. On the surface current carrying conductor is when you want to find the magnetic field strength at this position. When you want to find the magnetic field strength at this position, outside the current carrying conductor is at this position here, and inside the current carrying conductor is at this position. Now it was initially said in the case of electric field, we said that there is no electric field strength inside the charge producing the electric field. There is no electric field strength inside. For the case of the gravitational field, it was said that the electric field strength, the gravitational field strength is directly proportional to distance from the center when you are inside the earth. But for the case of electric field, the electric field strength inside the surface producing electric field strength is 0. And for the case of magnetic field strength, you're going to visualize it right down there. So here you're going to have outside the current carrying conductor, the formula is given as B outside equals to mu 0 I all over 2 pi d, where d is the distance here for RC, which is the radius of conductor, plus the distance from the surface here. So B is equals to mu 0 I all over 2 pi RC plus d. Now on the surface of current carrying conductor, we have B on the surface. BC is equals to mu 0 I all over 2 pi RC. So RC is the distance from the center to the surface. So from the center to surface is RC. So now let's visualize the case where you are inside the current carrying conductor. When you are inside the current carrying conductor, it will be B inside. B inside is equal to mu 0 I all over 2 pi RC. So 2 pi RC, you know that RC is a constant and this is a radius of the conductor, times R. R now is a variable, which is the distance from the center of the conductor. So these are the different cases. So the magnetic field strength inside the current carrying conductor is similar to magnetic field strength inside the Earth's surface, because both of them are directly proportional to distance from the center of the object you are measuring, with. So to conclude, we are going to have B is equals to mu 0 I all over 2 pi RC. All this is a constant and this is R. So it implies that the magnetic field strength inside the surface, inside the conductor, the current carrying conductor, is going to be directly proportional to the distance from the center of the conductor. So now this graph now here is going to be similar to the graph of the gravitational field strength of the Earth's surface. So B is going to be measured in Tesla, magnetic field strength is going to be measured in Tesla. You have inside the conductor BI, you have outside the conductor here, and this is RC, which is the radius of the conductor. So now this is in the case of a ferromagnetic material. A ferromagnetic material, the graph is as such here. Now in the case of a paramagnetic material, you have this graph here. And now what is a paramagnetic material? A paramagnetic materials, these are materials which can be magnetized easily but also easily lost in magnetic field once the magnetic field inducing the magnetic field, once the magnetic field strength inducing the production of the magnetic field is removed. So this is a paramagnetic material. Now for a ferromagnetic material, it is hard to magnetize but also hard to demagnetize, and this ferromagnetic material is divided into soft ferromagnetic material and weak or soft ferromagnetic material and hard ferromagnetic material. The weak ferromagnetic material are easy to magnetize, but they are not easier comparable to paramagnetic material, and they easily lose their magnetism, but they do not easily lose their magnetism compared to paramagnetic materials. And in case of hard ferromagnetic material, they are hard to magnetize and are hard to lose their magnetism once they are magnetized. Example is steel for hard ferromagnetic material, and for soft ferromagnetic material, example is iron. For paramagnetic material, example is copper. Now let's visualize again the case of solenoid, the magnetic field produced by the solenoid. The magnetic field produced by the solenoid, we need to know that there are two cases. You have at the center and you have at the ends. At the center, magnetic field is going to be given as mu 0 Ni all over L. So B center is going to be mu 0 Ni, where N is equal to N all over L. Now at the ends, you need to know that at the ends you see that at the center all the magnetic fields are close together. So here the magnetic field strength is going to be higher, while at the ends you see that the magnetic field are separating and they are disjoining. So it implies that the magnetic field strength is going to be reduced. Since it's reduced, B at the end is going to be half the B at the center. B at the end is half of the B at the center. So B at the end is going to be mu 0 Ni all over 2L. So B at the end is going to be half mu 0 Ni and small Ni, where small n is going to be big N, which is number of turns divided by the length of the solenoid. Now let's visualize circular coil. For a circular coil, the magnetic field strength for a circular coil, you have this current flowing circularly with a radius r here. So the magnetic field strength is going to be mu 0 I all over 2r, where I here is going to be the current flowing and r is the radius, the distance from the center to the core here, as shown here, and mu 0 is going to be the permeability of free space. Now let's visualize for Helmholtz coil, the magnetic field produced by Helmholtz coil. The magnetic field, what are Helmholtz coils? A Helmholtz coil consists of two identical magnetic coils. You have two identical magnetic coils here, having the same number of turn n. So in this case, for circular coil, if there are n number of turns, then the circular coils are going to be B is equals to mu 0 n I all over 2r. For Helmholtz coil, what are Helmholtz coils? Helmholtz coil consists of two identical magnetic coils having the same number of turns n, which are placed symmetrically along a common axis on each side of an experimental area, and are separated by distance equals to the radius of the coil. So this distance here, which separate the two identical coils with the same number of turns, is going to be the distance of the is going to be the radius of the coil here, r. So this r here is going to be this r here. So now when you have all this in place, and you are going to form your Helmholtz coil, then the magnetic field that is going to be produced by the Helmholtz coil is going to be equals to 0.72 mu 0 Ni all over r, and this formula has been proven experimentally. Now let's visualize the magnetic torque. What is the magnetic torque? Normally, by classical mechanics, magnetic torque is given as the force times the distance perpendicular to the direction of the force acting on it. So now let's say you have this north pole and south pole placed together as such here. Here you are going to have your electric current moving. So the current move in this direction. Since the current move in this direction, in order to know the direction of the force, we need to know the Fleming, to use the Fleming left hand rule. With the Fleming left hand rule, you have the index finger which point the direction of the magnetic field lines, magnetic field strength. You have the longest finger which points the direction of the current, and you have the thumb which point the direction of the force. When you use the Fleming left hand rule with your longest finger in this direction and with your index finger in this direction, you see that the thumb is going to be in this up direction, and this direction is going to be the direction of the force. So now let's visualize how the torque is proven. So this is from where the torque is proven. Note to know that this is the angle theta. Let's say you have the angle theta as such here. So here is going to be L sine theta. Please don't forget that the angle theta is the angle that is taken with respect to this along this line here. So the angle theta is not taken with respect to this position. It's not taken at this position. Angle theta is taken with respect to the surface here. So this is the angle theta here. So when you have this angle theta is similar to this angle theta here. So it implies that this L, you can say that it's going to be at this position is going to be L sine theta. So this is going to be the opposite. So this is the hypotenuse and this is the opposite. So this here is going to be L sine theta. So the torque here is going to be the force which is perpendicular to this distance. So it's going to be the perpendicular distance is going to be L sine theta. So torque is going to be the force times sine theta. So now let's visualize. We need to know that the force times sine theta. Now we need to know that the force here is going to be, in this case, the magnetic force, and the magnetic force given as BID, because the magnetic force is given as a big BIL, but in this case here the distance here L is going to be D here. So the magnetic force for the diagram above is going to be BID. So when substituting back in this equation, you're going to have torque is equals to BIDL sine theta. But the distance, the length times the width, DL, is going to be area. So torque is equals to BIA sine theta. So now for n number of turns, the formula for torque becomes torque is equals to BIA sine theta. So for n number of turns, the formula of torque becomes BIA sine theta. But this is a formula when you have only one number of turns. So now if the there exists an angle 90 between the force and the length d, then the torque is given as Bian. So now we need to know that point. The angle, this angle theta, is the angle with the length, the angle the force does with the object. So the parallel object as such here. It is not the angle with the horizontal. It is the angle the force does with the parallel object as such. So now let's visualize the movement of a charged particle in a magnetic field inclined at the angle theta. Initially, we had the movement of charged particle when the magnetic field was perpendicular to the motion of the charged particle. Now, in this case, the magnetic field now is not solely perpendicular, but has a component in a direction of motion of the charge. So let's say that this charge is moving with a velocity v here. So this angle here is going to be theta. So here is going to be the v sine theta, and here is going to be v cos theta. This is going to be the direction of the B field that is going to be produced. So a helical motion in this case is going to be produced. A helical motion is going to consist of two motions which have been bound together. It's going to consist of a circular motion and is going to be consisting of a linear motion. The circular motion will be due to the interaction of the velocity here. This velocity v sine theta is going to, and the interaction of the velocity v sine theta and the magnetic field strength. Since this velocity v sine theta and the magnetic field strength B are both perpendicular to each other, then they are going to produce a magnetic force. And that magnetic force is going to be what is going to cause the circular portion of the helical motion. And you have this v cos theta. V cos theta is what is going to produce the linear motion of. So this one is going to produce v sine theta, and the B field are going to cause a force that is going to cause the circular motion of the helical motion. And the v cos theta, since v cos theta is in the direction of the B field, so there is no magnetic force that is going to be produced in a direction in this horizontal direction. So it implies that there is going to be a linear motion solely due to the v cos theta. So now let's visualize a linear motion. With a linear motion, XAB, when this is going to move when the charge is going to move from A to B, XAB is going to be equal to Vx times T, but Vx equals to V cos theta. So XAB is equal to the period T V cos theta. Because the period is the movement when you finish all this circle and come out to this circle. This is going to be the period. So XAB is equal to the period T V cos theta. Now let's draw the circular motion. Since a circular motion implies there's a centripetal force, and that centripetal force will be due to the magnetic force. Now centripetal force will be equal to mvy. The vy is the velocity which is causing the centripetal force. So in this case you have mvy squared all over r, and now the Fm, the magnetic force is going to be equal to B cure Vy. The velocity is still in the y component here. So now it implies that mvy squared all over r is equal to B cure Vy. So r is equal to mvy all over B cure. So now, but we know that the Vy is the velocity in the vertical direction, which is V sine theta. So it implies that Vy is equal to V sine theta, r is equal to mv sine theta all over B cure. So now let's calculate the angular velocity. So we also know the centripetal force is equal to mass omega m omega squared r. So it implies that m omega squared r is equal to B cure Vy. Omega squared is equal to B cure Vy. So now omega, so it implies that omega squared, we can substitute down the value of r we have initially found here to be equal to mvy all over B cube. So when you substitute, you can cancel, and we're going to have omega is equal to B squared cure squared all over m squared. This is omega squared, and now omega is equal to the square root of B squared cure squared over m squared, which is equal to B cure all over m. So from here we can visualize what is the period. The period is equal to 2 pi all over the period. The omega is equal to 2 pi all over the period. Now we can substitute and place in this formula. We're going to say 2 pi all over period is equal to b cure all over m. So now period is equal to 2 pi m all over b cure. Now initially we have found that xab is equal to the period v cos theta. So we can substitute back in this equation to say period. Now we can visualize here that period is equal to xab all over v cos theta. So now when substituting back in this equation, we are going to have xab is equal to vx times t. So xab will be equal to vx into, when you substitute the period in this formula, 2 pi m b cube. So the distance xab that can be formed is going to be equal to 2 pi mv cos theta all over b cube. So this is the period, and we can also calculate the period from the distance, if the distance xab has been given, where the period is going to be equal to xab all over v cosine theta. So now this is the formula for these are the different formulae involved when you have a helical motion in a magnetic field. So from here we visualize all the different parts involved in magnetic field, and we say thanks for your kind attention. Please don't forget to like and subscribe for Science Video Makers. Thank you.